When we did our dimensional analysis on radiation pressure as force over area, what we said is that as the electromagnetic energy entered this box, it's completely absorbed, and what that means is that there's a transfer of momentum. Because this box was empty, that means that their electric and magnetic fields also store momentum. Now, it's actually a difficult calculation to make, but the result is the following, that the momentum, and this is a small p, so this is going to be the momentum per volume of space. So I'll just write here to indicate that this is momentum and not pressure. Small p is momentum. The momentum per volume is given by the time average of the Poynting vector squared, or time average of the Poynting vector, divided by the speed of light squared. Now, that's a difficult calculation to prove, but let's just see one of the consequences of that calculation when we compare how much energy is stored in this volume to how much momentum is stored in the volume. Well, we can see that the energy, du, that's stored in this volume is equal to S over C, and S, so we'll write this as times the volume, and S over C is equal to a factor C times the momentum divided by the volume. Because S over C, if you multiply by C's, you get C times the momentum per volume. And we can conclude here, this is actually, we just want, but we're multiplying it by dV, which I didn't write. So the dV's cancel. So our conclusion is that the amount of energy that was stored in this volume of space is equal to the speed of light times the amount of momentum that enters the space too. So electric and magnetic fields not only store energy, but store momentum. Now, given this relationship, we can also try to reconstruct the idea that the momentum transfer into this space is producing a pressure. So the way we'll look at that is as follows. We'll divide our momentum relationship by dt. Now, the rate of change of momentum is just by definition force. And if we divide by, on both sides, by area, so we get 1 over area, and let's take the factor 1 over c, du dt, then we get force per area, which is what we call the radiation pressure. Now, recall that the Poynting vector was the rate of energy change per time over 1 over a, and so we see that we get our result that we had earlier by a dimensional analysis, that if we just time average everything here, that the time average radiation pressure is the Poynting vector divided by the speed of light.